Good morning, everyone. This is Shashank Mittal. Currently, I'm a pre-final year student at IIT Varanasi, and I'm thrilled to share my journey as a Google Summer of Code contributor for Kubeflow. So today, I'll talk about how we enhance the Katib experiment APIs to add support for parameter distributions and enhancing the hyperparameter optimization for Katib. So hyperparameter tuning. So it is the process of optimizing the hyperparameter values to maximize the predictive accuracy of the models. So these are the variables that control the model training process. These include the learning rate, the number of training epochs, and the number of layers for the neural network. Even if you don't use Katib or a similar system for hyperparameter tuning, you need to run many training jobs yourself, and manually adjusting and tweaking with the hyperparameters is a bit difficult to get an optimal value. So that's where Katib comes into play. Katib is a core component of Kubeflow for automated machine learning, or as we call it, AutoML. It supports hyperparameter tuning, early stopping, and neural architecture search. So here's the architecture diagram. So the Katib architecture diagram for hyperparameter tuning mainly revolves around three main custom resource definitions. The first one is the experiment CRD. This is where we define the objective, the search space, and the search algorithms, which include Bayesian or random search, etc., and also the trial resources. Then the experiment controller creates the suggestion service and interacts with the suggestion controller and the trial controller. The next is the suggestion CRD that generates different sets of hyperparameters based on the algorithm specified by the user. And the third one is the trial CRD that runs multiple trial jobs for specific set of hyperparameters and calculates the objective and the validation accuracy of the model. So the main motivation behind this project was that currently Katib supports multiple hyper-optimization frameworks like Hyperopt, Optuna, etc. And these frameworks offer broad range of distributions. However, Katib only supported the uniform distribution for parameters like integers, floats, etc. So for many data scientists, this is very limiting, and many machine learning models require different types of parameter distributions. For example, learning rates perform better with log uniform distribution. So to address it, we introduced a few more parameter distributions. One of them was log uniform. This is for when the parameter values are varied logarithmically. And then the normal distribution for when the parameter values revolve around a central mean, such as the dropout rates, and the log normal distribution for when the parameter values vary exponentially. Now coming to the solution part, here you can see an experiment YAML, and from this, and there is the objective spec, then the algorithm name, and then the trial resources, and then the parameters, and each parameter has a feasible space. So let's focus on this part of the YAML, feasible space. This is where we define the ranges and the step value and the characteristics of the hyperparameters that we want to optimize. So earlier, the Katib only supported the uniform distribution by default, but now, due to the addition of this distribution field inside the feasible space, users can now specify the type of distribution. Also, there's the step field where we can specify the quantized value to sample out integers, and this combination of step and distribution is effectively mapped with the corresponding distributions for in the respective optimization frameworks like Hyperopt. So the benefits from this were that we were able to enhance the flexibility of the Katib project for hyper-optimization tasks, and we simplified the user configuration for with the new distribution field. And we were also able to align the capabilities with the advanced tools like Nevergrad. Thank you. Thank you. That's it from my side. This was my first presentation at KubeCon. Feel free to reach out on my socials. Thank you.